In the sciences, we often make lots of measurements of the same thing. Sometimes it's for reproducibility. We're trying to make sure we're measuring the same value, and then other times it's part of a protocol that we perform regularly. We perform a measurement every single day on different samples. Maybe we're in a QA/QC lab. Ideally, those measurements will all generate the same value, but in reality, there are going to be errors and uncertainties in those measurements. So part of the challenge here is to come up with some language that we use to describe these errors and uncertainties, and then also tools, in other words, math, to quantify them. That way we are more informed and are able to tell a better story about the data that we are collecting. So let's start off with a simple example here. I weighed a block of metal 6 times on my 2-place kitchen balance or kitchen scale. And then when I recorded those numbers in my notebook, I got 3.46, 3.4, 3.50, 2 times 3.6, and 6.35 grams. The manufacturer indicates that the block of metal should weigh 3.5 grams, and they said that it has a tolerance of 0.1 grams. So one of the first things we would think about is calculating the mean or the average. And the reason why we do that is because that value corresponds to what we refer to as the central value of the data set. So a central value, they are all centered around what particular value. And if I calculate that, we've done this before, so we don't need to go over it, I get 3.97 grams. So if we compare that number to the number that I was supposed to get, it's a little bit high. It's actually quite a bit high, well beyond the tolerance. And if we take a look at the set of numbers that I've got, something comes out, and it looks like I may have made either an experimental error in making that measurement, or I might have made a personal error. I might have transcribed these numbers incorrectly. It's possible that what I really meant here was 3.65 grams, and I just wrote it down incorrectly. Regardless of what that error is, we'll discuss later on how we could test to see if that can be excluded from our data set. It is clearly causing a problem with the mean or the average. It's shifting it higher than it should be. There's another way to determine the central value, and that's called the median. And the median is a nice tool to avoid, because it avoids being affected by outliers like this, but it's a little bit harder to calculate. It's a little more cumbersome because what it requires is that we first order all of the numbers in increasing order. So here 3.40, 3.46, 3.5, 3.5, 3.63, and 6.35. And then we look for the middle of this list. So I've got 1, 2, 3, 4, 5, 6. The middle of the list is right here. If I have an odd number of values, then it would be that value that's right directly in the middle. Since I have an even number of values, it's going to be midway between these two, which coincidentally is 3.5. So notice how the 6.35, the outlier, doesn't come into play in that calculation at all, and I can get a median value, which in this particular case is really close to the expected value. So 2 ways to calculate central values. The median we don't use very much because it's cumbersome, and the mean is actually very easy to calculate, and it comes into play in later discussions when we start talking about normal distributions. So we saw that there are these two measures of determining the central value, mean and median. So that's median. And I want to highlight several measures of spread, or the variability between a data set. So we've got our set of data from the previous slide, and all of these numbers are in grams. The range is pretty straightforward. So there's range is it is just the max value minus the min value, which in this case, if we look at the 6.35 and the 3.4 as the highest and the lowest, we see that range is about 2.95. Notice it is fairly affected by the outliers. In fact, it's going to be significantly affected by the outliers, and it doesn't tell us anything about frequency. So, for example, we've got two numbers in here that are the same, but we would never know that by just looking at the range. The standard deviation does that for us. It actually looks at it's calculated by looking at the average value, so the mean, and looking at how each individual element differs from the mean. We don't care about the equation. We just need to know that we can calculate it with Excel or some other sort of tools. I'm going to say just write down the number here. For us, it's 1.2, and it also is in units of the same units as we report our masses in this case, which would be grams. And that's actually one of the big benefits. So this is a benefit of using standard deviation as a measure of the spread. It not only tells us something about the dispersion and the frequency of those dispersions. So the fact that there are two 3.5 values in here does get roped into the value that we've calculated for standard deviation, but it also has the mass, the same units. Variance is essentially the standard deviation squared, and you would think that is not something that we would calculate very often. It turns out that it's very useful for us in propagation of error, because it turns out that variances are additive. You don't need to understand what that means right now, because we'll see that when we talk about error propagation. In our case here, the 1.4 is the variance, but because it's the standard deviation squared, the units also get squared. So we get these weird units called grams squared, which doesn't make a heck of a lot of sense in a physical sense. So the advantages of variance are that they are additive, but the units are weird. So those are the three types of spread that we would see commonly in analytical chemistry, and the two types of central values. The really important ones are mean, we use that frequently, and standard deviation, we use that frequently. So let's talk a little bit about the different types of errors that we can find in making measurements. It turns out that we can organize errors into about 5 categories. First one would be sampling. So let's say that we are making measurements of pollution in a stream. So you've got some sort of stream, and there's a factory that is spewing some sort of pollutants in the into the stream, and you want to know how it's handling, how it's affecting the people that are playing in the stream downstream. If we do our sampling right here versus right here, we're going to see significant differences because the concentrations right at the source are expected to be higher than the concentrations that are going to be downstream after there's a chance for dilution or maybe some sort of runoff if there's actually another part of the stream right here. So part of that would have to be taken into consideration in the experimental design if it is intentional for us to sample at the point source or farther down the point source. But if we don't control for that, it becomes an error in the actual measurement. So we need to know what we are doing and be aware of how we're sampling. The method that we're using it can also be a source of error, and this comes into play. Remember, if we have a signal from an instrument, that signal is going to be proportional to the amount of material, and then there may be some sort of offset. So notice how this is a straight line that we've the linear expression, and if we have not calibrated our instrument properly, then the slope here is going to be different, or maybe the offset is going to be different. And that calibration, a poor calibration, is going to lead to a poor relationship between the two values that we're interested in looking at. So when we design a method, ultimately what we're interested in is having the signal from the instrument tell us something about the amount of material that we have. And if K and B in this particular case are not well known, then we are introducing a certain type of error. The measurement tools. So measurement can also be a problem. So think about a volumetric flask versus a graduated cylinder. So if you've got a graduated cylinder that has gradations of only 1 milliliter, where we have a volumetric flask that is precise, or I'm sorry, a volumetric pipette that can give us precisely 1.0 milliliters. If we have a meniscus in here and that's in between the 1 and 2 milliliters, we don't know precisely whether it is 1.5 or 1.4 or 1.2 milliliters. The volumetric pipette is designed to give us that precise amount. So using the glassware or the tolerance of the glassware plays an important role in the types of errors that we get as well. Lastly, there are personal errors. So these are what we typically call the human errors, although they're not always mistakes. So like in the previous example where I wrote down 6.35 grams in my notebook instead of 3.65 grams in my notebook. So that would be a mistake. But also, if we're talking about a titration, if you remember in the titration, that endpoint color it needs to be a certain shade of pink in the standard titration. If I can't see pink colors because I'm red-green colorblind or something like that, then it's not a mistake. It's just an inability to determine that when I'm supposed to start. So these are all different types of errors. There's that we might be able to control. There's one last set that we can't control. We would just lump these into random random errors that that are happening beyond our control and are not well defined. So we can break these 5 errors into, or we can clump them into 2 categories. All of these that I've circled are determinate errors, because we can determine their sources, we can determine their identities, and we can do something about them. The one that we have over here is indeterminate, because we can't do anything about it. It's going to be there whether we like it or not. We won't be able to minimize it below a certain value, and so we're stuck with that. So one of the really important take-home messages from this is that there will always be error in a measurement. There will always be uncertainty in a measurement. We can't avoid those 2 things. Now, it turns out that these determinate errors speak to the accuracy of the measurement. If we have large amounts of determinate errors, then they are shifting the measured value away from the actual value. So this is affecting our accuracy. Random errors or indeterminate errors are affecting our precision. So the spread of the measurements, even if we can control for all the determinate errors, the indeterminate errors are going to remain and influence the precision of our measurements. Okay. So 5 different types of errors. We can categorize them into determinate and indeterminate classes. The determinate errors influence our accuracy, and the random errors or the indeterminate errors influence our precision. The last thing that I want to mention here is the subtle difference between error and precision. The subtle difference between error and uncertainty. Errors are going to be associated with the determinate errors and influence and are telling us something about the accuracy. So when we're talking about the accuracy of a measurement, we're going to refer to errors that influence the accuracy. And uncertainty is referring to the range of values that we can actually observe, and that is related to the precision or the indeterminate errors. 5 different types of errors: determinate versus indeterminate. Notice how they are associated with accuracy and precision. And then we have these last 2 terms, errors and uncertainty, which are used for the 2 different categories.